The topic of my thesis is called Technical and Economic Characteristics and Predictability of the Selective Laser Melting Process. So I give you a short introduction to selective laser melting, then I will tell you what was done within the technical characterization of the process, what was done within the economic characterization, what is behind the topic of predictability of the selective laser melting, and then I give a short summary of the thesis and its main results. So to start with the introduction, I like to show you what SLM is. It's a layer-based process where a laser melts a metal powder into a solid part. Basically, the video on the right is supposed to work, but unfortunately it doesn't. However, I proceed on with the next slide. So why is selective laser melting important to industry? It offers quite some interesting opportunities in terms of freedom of design, weight reduction, functional integration, part reduction, customization, lot size independence. And a further goal, which is also followed by Siemens, is to establish a decentralized production setup where you have printers close to the main places of demand, which helps to reduce delivery times and time to markets, especially for spare parts. So these are nice, good opportunities, but however, the selective laser melting process is challenged, as you can see on the left-hand side on the picture, by multiple process influencing factors. This Ishikawa diagram was made by Olaf Rehme. He counted 157 process influencing factors which are partially uncontrollable or unobservable, which leads to the question if this process is capable to meet industrial needs in terms of its capability to provide mechanical properties as required in industrial standards. And the second question is if the process results are reproducible, which is very important, especially for spare part application. When you printed a good part once, then you want to print it again. So there's an alarm, however. The technical characterization, well, the problem statement is when you try to figure out the mechanical properties of selective laser melted parts in related literature, you will find that most material characterizations are based on a single batch production. So they produce one time a specimen, they test it and they say these are the properties, but however we don't get information on the process stability over time. You can also access the material data sheets by open equipment manufacturers. These contain disclaimers that the material properties are not guaranteed, so these values are not reliable. And in industrial guidelines, they provide you ranges of material properties, however they don't mention the exact test setup, so we also do not know how stable the process is from these sources. So this is basically the reason why it was investigated. So the technical characterization compromises 3 steps. The first step is an analysis on normality to derive the distribution profiles and distribution parameters of certain features. This is then followed by an analysis on process stability, and which gives us the answer on the state of statistical control to see if the process is stable. And at the end of the chain, we can then check on the process capability to see if the process is, from a statistical point of view, capable to provide material properties as they are required within the industrial standard. So the analysis on normality compromises the production of 15 production batches. Those production batches are done in the same material on one machine at one location. So we want to see how does the process deviate over time. So this was one time done in stainless steel and one time in aluminium. Here you see the batch occupation. We have like 7 specimens, 5 specimen sets on 5 different platform positions. Every specimen set compromises 7 different specimens. So to leave no platform position blank, it was rotated on each 5th batch to see if there are position dependencies on the mechanical properties. Here you see the single specimens which are contained in one batch setup. So we have 5 times vertical orientations, 45 orientated specimens, horizontal orientated specimens, and specimens which are fabricated close to the final test geometry. Then additionally we have density cubes which are used for Brinell and hardness tests, and also Charpy impact bars. So those specimens have been manufactured under very stable process boundary conditions with uniform procedures throughout the entire process chain. And well, different numerical and graphical analysis methods were used. So the graphical approaches compromise basically a graphical judgment on the appearance, which was scored with a good fit to a normal distribution with 2 points, with a moderate fit with 1 point, or with a poor fit with 0 points. And the same scoring system was applied for the hypothesis tests. And when there was no rejection on the H0 hypothesis, 3 points were given. When there was a rejection, no rejection after outlier removal, there was 2 points. And when it was rejected, it was 1 point, 0 points, excuse me. So to give you an impression on the graphical procedures, here you see a control card which lists all the tested values over time. Once a value is located outside the 4 sigma interval, which is basically a 95.45 probability, then it will be not considered within the statistical evaluation. Here you see the histograms which are used. The histograms just plot the probability density of certain classes. It's overlaid with a kernel density estimation and with a normal distribution line to see how good the tested population fits to a normal distributed one. Here, as you can see, it's quite different, so 0 points were given. Then the second technique was so-called Quantile plots, where it's supposed that the values are following this normal distribution line closely. This was the second criteria which was used. Here again you see strong residuals, so here also, for instance, 0 points were given. And the third visual technique was then so-called box plots, which shows you the quantile distribution of each feature. And basically, when it's normally distributed, it should appear like this. So this looks very differently, and so each feature was judged by giving points to each plot according to its appearance, and these are summed up. And when the sum reaches 7 points, it's considered as normally distributed. So there are many plots, so I don't go through all of them. I will just sum up the main results. Within stainless steel, there were 25 production runs necessary to derive 15 good ones, which gives a process reliability of only 60%. And overall, 87 outliers were removed prior to statistical consideration. Overall, only 9 of 22 orientation-specific features were found to be normally distributed. For aluminum alloy, only 2 batch repetitions were necessary. The reliability was at 88%. 59 test results were considered as outliers, and 15 out of 22 orientation-specific features are found normally distributed. So, if it was found not normally distributed, a 3-parametric Bible distribution was used to fit the tested population as good as possible. So with those distribution parameters, we can go then the next step to the statistical verification on process stability. Therefore, the method of Shewhart control cards is used, which investigates the stability of the features, location, and dispersion parameters. Here, each batch is averaged into one single value, so it's based on rational subgroups, and the criteria is that you don't have a certain violation visible within those control cards. So here you see a typical control card as it was tested out, and you can see there are some violations of the random scattering region. So basically it was found for stainless steel that no feature is in a state of statistical control. In aluminum, it looked pretty the same, where 20 out of 22 features are found out of statistical control. So both materials were mainly unstable regarding their process location parameter. The process dispersion was quite constant. I'm having how much minutes left?
10 minutes left.
10 minutes left, thank you. So the third step was then the check for process stability. Here the calculation method is predetermined by the process stability as it was calculated in the previous step. And as limit values, the material thresholds which are provided in industrial standards were used. So basically the finding here was that the process is mainly capable to provide the material properties as they are required in industrial threshold, in industrial standards. There are only few exemptions for aluminum alloy. It was found that the process is not capable for the feature of break elongation in condition F, which is basically unheat treated. Yeah? And for stainless steel, it was also found that there are restrictions to capability in terms of 40% break elongation and Brinell hardness. So these are the only features which were found to be threatened to be violated by the material properties. So overall, the main result of the technical characterization is that the selective laser melting process is found capable, but out of statistical control. And this out of statistical control has certain implications. From a process control perspective, there are reasons for non-random variation in the process. And these reasons for non-random variation are unidentified and they remain persisting in the process. And so if we want to do heavily loaded structural or safety related parts, the consequence is that we have to do 100% testing on each process result. We have to verify each process result if the main material properties are still maintained. And this causes costs for quality control, which are mainly unfigured in related literature. To estimate such costs, you need to have processing times. In literature, processing times are mainly considered for certain demonstration parts. Then you need to have process costs. Those process costs are also in literature mainly related to demonstrating parts. And the costs for quality control are mentioned in some publications in terms of, yeah, you should consider there could come certain quality costs on top, but they are totally unfigured. So within the economic characterization, the main question is how much cost for quality control will emerge from this process characteristic. And so the economic characterization comprises 3 steps. The first step is a time study on the entire process to derive average processing times. Hereupon, the total cost of ownerships can be used to derive an hourly machine rate, and when you have the machine rate and the processing times, you can then calculate the initial cost for quality control, which is basically the setup costs. And you can also consider the recurring cost for quality control. So basically here, within the time keeping, the operating asset, the SLM machine was main subject of investigation. So when we want to start a process, we need the data, we need the powder, then we can build the part, and after this we have to withdraw the part and the plate, we need to separate, we need to reprocess the plate. Then we can put it back into the machine, we need to reprocess the powder, and we need to take away all the process data from the machine that it doesn't overfill. So these are basically the 3 main cycles to get the machine through one operation cycle and ready for the next one. So here, these are several time types, which I don't go into detail now. They are just a measurement for process optimization. So here you see the distribution of the time times throughout the several process steps. The main important thing on this slide is the processing times here on top for the process preparation and post-processing steps. Because these times will reoccur for every process that you conduct. And so I call these ones peripheral activities, which sum up to nearly 9 hours, which means if you want to start an SOM process, you need to consider an entire day for process preparation and post-processing. So when we have the average processing times, we have to consider the hourly machine rates, which was done here. The hourly machine rate is at 32 euros, where basically more or less 3/4 of the costs are generated by the machine and related software contract, which is quite high. So with those costs and times, I was then capable to calculate the setup costs for a basis of quality control to derive process location and dispersion parameters. And as you can see here, the production costs are basically determined by 2/3 for specimen post-processing and specimen analysis. So these costs are quite high. It's 100,000 euro you have to invest for each material system or each parameter set. And even if you have invested those 100,000 euros, then you are still followed by recurring costs for quality control, as you have to test the process result on each production batch. And here it was found that those recurring costs constitute about 50% of the recurring fixed process costs, which is quite high. And if you consider this in addition to the initial costs, it's just a very, very high amount of money to be invested, which needs to be considered as business case threatening once you don't consider such costs upfront correctly. So the main conclusion here is we need an alternative approach for quality control in selective laser melting. And so one approach was the usage of so-called process monitoring data, which is acquired through photodiodes and high-speed cameras, which are installed coaxially to the optical paths. Basically, the process refulgence, once the laser interacts with the powder material, is guided through those sensors, and there are two systems which give you certain data. The one is called QML pool, and the other one is called QML pool 3D. To give a short explanation, QML pool lists a mean value of the process refulgence and a variance for each layer. And it gives you a so-called signal curve for the camera system and for the diode system. And so what should be done with it? It should serve as a basis for comparison once you manufacture identical parts. And QML pool 3D goes one step further. It takes the signals and correlates those with the scanner position, and basically recreates a signal map which gives you a layer image. So the signal is just measured, it's transformed into a grayscale value, and it's then allocated to a pixel grid which is closest to the scanning position. So at the end you get a layer image or a layer signal map which represents a layer of your part. So with one part, it has thousands of layers. You get thousands of images for both systems. And the issue with this data is with QML pool, well, you can use such curves for comparison, but basically no one tells you which deviation bandwidth is acceptable. So if it's just a small difference, is it okay or not, or how high those peaks may be. So the judgment criteria is missing, and the same applies to the QML pool 3D data. You can use certain grayscale intervals as indicators for defects, but if you have only few indications or a lot of indications, it's totally dependent on your personal setup, and there are no fixed analysis settings in the market. So also here the judgment criteria is missing. To address this problem, several steps were undertaken. It was a graphical analysis undertaken for the QML pool data, where the main finding was that when we apply a normalization procedure based on the variation coefficient, it helps to separate the curves. Then it was machine learning applied on the QML pool data, however with not much success. So I tried then machine learning on QML pool 3D data on the images, which was quite promising. And so now I will just tell as a final step some backgrounds to this machine learning. Machine learning is basically divided in three fields of computational science. Here I just focused on the purpose of process classification, so which is done via neural networks. Neural networks are basically a calculation sequence within computers, and it works as follows. You provide a feature to so-called input neurons. Those input neurons provide the input values to the next layer through so-called connections. Each connection has a weight. It can adjust its weight. And so the input sequence in the first layer makes a sequence in the second layer, which gives you a certain sequence in the consecutive layer, which then gives you a prediction of the neural network on the outcome. So the learning mechanism is with a neural network solely by weight adjustment of those connections. So when the neural network derives a prediction, it will then look at a so-called label and make a comparison of the label to its prediction, and it will then calculate back the prediction error and adjust its weight. And when it's done this one time, it will take the next set of data, process it through forwardly, derive a prediction, it will compare the prediction with the so-called labels, and it will then backpropagate the weights to derive a better prediction on the next time. So this is just another visualization how neural networks operate. You have multiple data points, for instance our layer images. Each layer image is a data point, it has certain features, and it has a label which I give to it. And then the neural network takes those features, it runs its classification algorithm, it derives a prediction, and then with the labels which are coming with the data, it verifies its prediction and then adjusts its classification procedure. So convolutional neural networks, well, I just overjumped this through to time purposes, use convolutional techniques. Convolution is a method of filtering the input image to a significant features. Here I show you how a convolution of a layer image looks like. This is the layer image. It will be transformed by the neural network throughout multiple convolutional stages. And here the technique is that the machine learning algorithm adjusts its filters in a way to create images upon which it can make good separations on the process result. So it basically learns how to prepare the images to get a purposeful differentiation on the outcome. So very important for machine learning is you have to select significant data, and so 4 classes were selected. One which represents good mechanical properties, one class which is mentioned as average mechanical properties, and one which is considered as bad mechanical properties. And we also had one so-called mapping failure which occurred throughout the tests. You will see it in the next slide. To train the machine learning environment, the images need to be pre-processed. They were just normalized by the variation coefficient. They were then cropped, and then they were randomly rotated to avoid positioning-based bias on the outcome. Here you see 4 exemplary images for the classes we had. This is the mapping failure, and you can see there's a clear difference between the data. And so overall, 18,000 layer images were used for training. 10,000 training epochs were applied, and 1,000 test images were withdrawn. Here you see the network topology. I will also jump over this. Here, these are the test results, and those test results were quite good with prediction accuracy of 99.7%. So, however, these test images were taken from the stack of the training images. They come from the same specimens, so there was another validation run carried out. so therefore different specimens were allocated, and overall 9,280 layer images were used for validation, and here the neural network was capable to provide a validation accuracy of 98.9%. So here you see some examples of correct predictions, or also some examples of false predictions. However, the prediction accuracy is quite good, and so the generated model which was created enables an objective judgment on the process monitoring data. It thus provides a missing link for monitoring data evaluation. It's quite quick. It analyzes an image below 0.10 seconds, and it could be used for closed loop control system. It can be further fine-tuned, and it will be very helpful to reduce quality-related costs, as you don't have to destructively test specimens anymore. So it's the first of its kind in selective laser melting, and so I give the summary of the entire presentation. Within the technical characterization, the process was found capable but out of statistical control, so hence frequent quality control is required. Within the economic characterization, those costs for frequent quality control are found to constitute 50% of fixed process costs, and also the setup of such is very cost intensive, and as a solution, a machine learning model was developed which enables the purposeful classification on the process result based on the process monitoring data. So as a last one, the contributions to the body of knowledge, the findings of the statistical or technical characterization were published last year within the journal, International Journal of Advanced Manufacturing Technologies under the title Statistical Assessment of Mechanical Properties of Selective Laser Melted Specimens of Stainless Steel. And by now, the second paper, which treats the machine learning topic, is submitted to the Rapid Prototyping Journal. It's currently in the post-review stage, so I already received the review results and implemented those and sent it back. So it's basically run under this manuscript ID, and I'm waiting for the happy announcement that they accept the paper. So then, thank you for your patience. I think I over excused my time. Welcome.
And I would really like to know the topology you've chosen for the DCNN.
Yes.
Could you just explain why you choose exactly this topology? So what was the reason?
Yeah.
And, so because I think it's very fast, which I really I think that is one of the big benefits. But let's say the complete picture of the DCNN, which was a little bit short on the presentation, but I absolutely
So it's basically it's a very difficult topic. So I started the network topology on an example on handwritten digit recognition, which gives a very similar approach to the problem that we have. So when you want to computer identify handwritten digits, you have grayscale images. You have certain output classes. In handwritten digit recognition, you have 9 different classes. And so my first approach was to see what was already done and which are the solutions. And so it's like the hello world example to machine learning. And so I was starting with it, and I adapted this model to smaller classes, and I was playing with the filter sizes to see how the outcome is. However, I recognize that especially within the validation runs, the initial models that I had were not capable to exceed 75% validation accuracy. And then it's a process of try and error. You can play with the filter sizes. You can play. There are a lot of variables that you can adjust. And so at one point I just said, okay, there are those deep neural network structures which are very popular for difficult classification tasks, where you try to separate faces and different objects. And so I tried to deepen the network structure with smaller filter sizes, which resulted in very good results. And so, yeah, I stopped it. So I'm not in a position to say that this is the best setup or best network topology, but it provided the best results within my test scope.
Yeah, earlier on you were talking about the fit, and I wasn't clear on how you were deciding what was good and moderate and poor.
Yeah.
How do you determine?
Which is very difficult in statistics, is how to test on normality. Because the graphical procedures are very sensitive to the way you prepare the data. So, for instance, I could have chosen to make only 4 classes of bins, right? It gives you then a small one here, a large one there, and a small one here, and it would it would look like as it is normally distributed. So I tried to apply different techniques on graphical visualization to get to look at the data from different perspectives. So basically, when it looked like this here, it is considered as a bad fit. So I did not show now a good fit would look like when the red line progresses closely to the black one, right? When the kernel density estimation is close to the normal distribution line. So the normal distribution line is simply plotted on the calculated mean value and the standard deviation of the population result. But as you can see, the population is not normally distributed here. And so when I was sure that it's not normally distributed, I scored with 0 points. When it was really good aligned, I gave it 2 points. And when it was not perfectly aligned, but still good enough, it was 1 point. And so the criteria was to merge the points of the histogram appearance, of the quantile plot appearance, and the box plot appearance with numerical tests, which are hypothesis tests. So they are totally off any subjective judgment. They just read the data and they calculate the probability to being that the data originates from a normal distributed population. And then I merged those points to a total score. I try to go back again, which is here written. So for each graphical plot, 2 points in best case can be given. So I have 3 graphical assessment, which gives you at maximum 6 points. And normal distribution was only concluded when it exceeds 7 points. So at least I need all 3 to be a good fit, and I need 1 numerical test to confirm it's to be normally distributed. Or I need 2 numerical tests to confirm a normal distribution and 1 moderate fit within the graphical plots. So this was the approach to avoid like subjectivity on the judgment.
So it had to get 7 points to be considered good.
Yes.
And the moderate was between how many points?
Moderate. Well, it's for each plot on each feature. So
Okay.
so when I get, let's say, tensile strengths for vertical orientation, ultimate tensile strengths, then I look at the histogram. If it's a good fit, it gets 2 points. Then I look at the quantile plot. If it's a moderate, let's say it's a moderate fit there, it gets 1 point, so I have 3 points. So I look at the box plots, doesn't fit, it gets 0 points. It stays with 3. Then the chi-square test says, well, prior to outlier adjustment, I assume it's normally distributed. I get 3 points on top, it makes 6 points. And now it's on the Shapiro-Wilk test. How will it score? Will it say yes or no? And then, so the scoring system has a slight stronger tendency to reject a normally distributed population, which is caused by the scoring system, but it's just a small tendency, about I think 48 to 52%, because you have different combination opportunities in theory how this 7 points can be reached.
You concluded that you have an out of statistical control your X bar chart and R chart, you picked samples at 15, you picked left samples at out of 15 populations.
Yes.
Did you consider reducing it to 5 to have more samples and see whether it will be statistically?
It's already so in the analysis for stability. It's on rational subgroups, so it's averages from each bench. So it's already averaged.
Now, if it were possible, because you are using a linguistic scale of 3 for scoring system. 1, 2, 3, that's bad, good, I don't know.
Yes.
In engineering, a linguistic scale of 3 is too small. You should have considered a linguistic scale of 5. It's not a question, but even if you cannot consider it, develop a claim to counter it and let it be. I hope you understand what I'm trying to say.
No, I didn't get that, honestly.
Okay, let me come back. A linguistic scale of 3 is too narrow to prepare a judgment. You know, when you were saying
all right, yeah. Yes.
It should have been a linguistic scale of 5. That is the minimum. Now, if the nature of the work does not permit you to use 5, you should explain why you are sticking to 3.
Yes.
Justify.
Justify.
Yeah. It's okay. Yeah.
It's not a question, but for you to, because when your assessor is reading,
yes,
I don't want him to pick you from there.
Yes.
If you have not justified.
It's explained in the thesis, but I get your point. Yeah. So. Yeah.
Now, when you were presenting, you said your contribution to the body of knowledge, you showed us the 2 articles.
Yes.
I think this is a PhD work. The articles are your milestones. Your contribution to knowledge is a section that will tell us the hypothesis you are presenting that will add to the theory, but to the theory that we already know. So, from your aim, and you go back to your seat, in your research seat, from your aim, your objectives, your method, you can join in and come up with your contribution to knowledge. You can also look at those articles you have published. Look at the germane issues you are raising. Then from there, you can also come up with your contribution to knowledge. But make sure that anybody that is reading it is also viewing it with your aim, your objectives. So, in a nutshell, make it coordinated.
Yes.